Good afternoon, everyone. How are you all? So, first of all, don't get confused by the name. Uh, so, today we will start semiconductor physics. So, first, I will say we will wait for some 2, 3 more minutes for the students to join. Uh, After that, we will start. So, if you are watching it on recording mode, you can skip first 1 or 2 minutes because we are waiting for the students, more students to join. So you can skip initial few minutes. So today's lecture is again going to be very important. This is about semiconductor physics. Most of the times in the JE exam, one at least one question is there. Always, it is a fact that always there will be a question from semiconductor physics. I am talking about JE mains. And if I talk about NEET exam, you will see more number of questions, like one or maybe two questions from this particular chapter. So till now in the JE exam, transistors were there in the curriculum, but now from this year or the in the notification of this year, the transistor part is removed. So it's a quite easy now for you because transistor was a lengthy part. Okay. So till now, what we can say, you have studied about modern physics, the atoms, the photoelectric effect, the nuclear physics, and now semiconductor physics. So before we start our discussion, let's see what is the content of this chapter. Okay. So what's inside the lecture? First of all, we will see what is semiconductor, like what is the use of semiconductor, and next we will study about what are the types of semiconductor. Then we will study about PN junction, then biasing of PN junction, VI characteristics, rectifiers, some special purpose diodes, logic gates, and then some previous year questions. In between, we have some concept test. The concept that I am teaching, we will discuss it. Okay, so it's time to start. First of all, what is energy bands in solid? So in this particular side, we are just going to discuss, rough discussion is there. Rough discussion means we will discuss few things that you already know. Okay. So what are those things? If I start, for example, in the atoms chapter, what you have seen that every atom or in every atom, there are some energy levels, right? You know that. Like if I draw an atom, there is a nucleus, positive nucleus obviously, and then around it electrons revolve like this. You can see the electrons revolve. Clear? This is the basic idea of an atom. Now what you can say, the electrons are revolving in these orbits, and now if you say these each orbit, like this one and this one, these each of these orbit have different energies. Like if I say the electron is in this first orbit, then it has some different energy. If it is in second orbit, it will have some different energy. That means the energy, these are generally known as energy levels. I think first statement clear. You can remind it from the atoms chapter of your study when you studied it, atoms chapter. Now this is very simple. Now if you go for the structure like shell structure, like 1s 2s, something like that, the same follows there. Okay. Now this is an isolated atom. Now come in solids. This is the idea of the isolated atom. Now if I come in solid, this is for what? Isolated atom. Sir, what is the meaning of isolated atom? Isolated atom means an atom which is placed separately, not connected with anyone. Now, if I say for solids, these energy levels are definite. Now, if I talk about solids, you can see here, like if I say in solids, you can say the atoms are packed very close to each other. Can you imagine that in a solid atoms are packed very close to each other? So in that situation, the diagram of the atom will look like something. This is the nucleus and around which electrons are revolving. Look at that. This is something, and this is another atom around which electrons are revolving. Now you can see that when these two atoms are placed very close to each other, the electrons orbiting in these orbits or in outer orbits, like this is electron which is revolving, these electrons will interact with each other. And when these electrons will interact with each other, the isolated atom has some different energy for a particular orbit. Now, due to the interaction with another nearby atom, this energy may change. This energy may change, and this change in energy may increase or decrease. Are you getting my point? What I'm saying, for example, if you see, like for an atom, there are, like you can say, electrons are filled something like that in 1s, 2s, 2p, something like that. These three shells are filled. For isolated atom, if I say there is definite energy for 1s, definite energy for 2s, and definite energy for 2p. They have some definite energy. This is energy for 1s, 2s, and 2p. Each of these shell have some definite energy, and this is fixed value. Any particular value, maybe it depends on the atom. We can't say a particular value for that, but it will be a fixed value. Now, when these atoms come close to each other, this value is not fixed, is not anymore fixed. Why not fixed? Because due to the interaction with the nearby atom, this energy of the electron may increase or decrease depending on the interaction. Are you getting my point? So what I say now, I will ask one very simple question to you. For which of the orbit the interaction will be more? You will say, sir, for outer orbit interaction will be more. They will interact more. And for inner orbits, the interaction will be less because they are far apart, and outer orbits are closer to each other. So the electrons in outer orbits may interact more, but in the lower orbits or inner orbits, it may not interact more. So what happens due to this interaction? The energy of the electrons varies. So for which electron energy will vary more? The higher the electron, more will be the variation in the energy. Now, if I say for 1s, for isolated atom, there was only fixed value. Now here, the value will not be fixed. It will vary. It may increase or decrease. So let's suppose I'm showing it. Now, there may be two values or maybe three values, maybe more values, more than that. So for the representation purpose, I'm showing that there are different values. Clear? Now for 2s, if I say this is the higher energy level. So here, this is for 1s, and for 2s, there will be more interactions, so more variation will be there. So more variation will be there. This is for 2s. I can draw it. I'm just giving you an idea. I'm not saying how many lines, how much variation, how many variations will be there, but I'm just showing you what is the basic phenomena behind it. Now, if I say, you can clearly say that for 2p, 2p is again another higher level. So for 2p, the interaction will be more. And if interaction will be more, that means variation in the energy will also be more. So what happens now, coming back to the topic, what's happening here? This is for 2s, I will say, sorry, 2p. Okay. This, what are these lines representing? These lines are representing the energy levels of what? Electrons in a particular shell. Clear? So after this representation, what is the our topic? Our topic was energy bands in solids. So band means, you can say that band is something, a group of something. Like you can say, mostly you have heard the musical band. So musical band is what? Is a collection of peoples playing different instruments. Someone is playing guitar, someone is playing piano, someone is playing flute, or whatever the instruments, I don't know. So band is something collection. So here energy band means collection of energy levels. What is the definition of energy bands? Is the collection of energy levels of what? Of a particular shell. So you can see that this is a collection of energy levels of which shell? 1s. This is the collection of energy levels of what? Of 2s. Can you see that? This is the collection of energy levels of 2s, and this is the collection of energy levels of 2p. So this collection of energy levels is called band. So if someone asks you what is the energy band, you can clearly state that the collection of energy levels of electrons in a particular shell is called energy band. So these all are the energy bands. Energy bands. I think this statement is clear. The process is clear what's happening here. For isolated atom, the energy levels are fixed. But for solids, due to the interaction with nearby atoms, the energy levels may vary, may decrease or increase from the fixed value. If they increase or decrease or they change, then for which of the shell it will be more? The interaction will be more or the variation will be more for the outer shells. Clear? Because I think you can see that why it is more, because the electrons are closer to each other. Okay. So collection of these variation of energy levels is called energy band. I think everything is clear in this particular topic. Now I have placed all these things in a slide beautifully. Now you can see. Just check what you have learned. Okay. An atom has defined energy levels for every shell. You know that. I have described it for isolated atom. Now again another point. But in solids, when atoms come close to each other, there is a shift in the energy levels of particular shell. Now it's time to take the notes. This is a section where you can write down everything. What I'm saying, but in solids, when atom come close to each other, there is a shift in the energy levels of the particular shell. You know that. Why the shift in the energy levels? Because of the interaction. Next, for a particular shell, energy levels of a particular shell may rise or fall. I told you it may increase or decrease. Clear? So the collection of energy levels of a particular shell due to the interacting atoms is called energy bands. I think the statement is clear to you. The variation हुआ, energy levels में variation हुआ, the collection of that variations is called energy band. Now, very important point. Energy levels of outermost cells are most affected by the interactions of closely packed atoms or in solids. All these things I have described already. That outermost shells have mostly influenced by the nearby atoms. I think everything is clear in now till now. Now, after describing the energy bands, we are moving towards another section which is very important for us. Like, what are the famous energy bands? So we have two very famous bands. One is valence band, another is conduction band. So what is valence band? Listen, we will see the definitions, but first of all, you need to listen to me. If I say, what if I say that in a particular atom or in a particular solid, there are a lot of atoms of the same type. I am saying that an atom fills the electrons up to 2p, like 1s, 2s, 2p, up to 2p, it is filled. Up to 2p, it is filled. And after that, all are empty shells. Are you getting my point? What I'm saying? 1s is completely filled, 2s is completely filled, and 2p is either partially filled or completely filled, doesn't matter, but it is filled. And after that, all others are empty. Clear? This is, I'm deciding for an atom, for an example, let's suppose. Now, what is valence band? The band which is filled with electrons is called valence band. You can see the definitions. The highest energy band which is filled. So you can say out of these three, which is the highest? You can say 2p is the highest. You can say 2p is the highest band. Which is filled, you can write it here completely or partially, doesn't matter. So how many bands are there? 1s, there is a 1s band, 2s band, and 2p band. So which band is known as valence band? The highest band. So 2p is the valence band. Are you getting my point? Now, what is the conduction band? Next is what? Conduction band. I think definition is clear. Conduction band, if I say the band just above the valence band is called conduction band. After that, all others are empty, like 3s is empty, 3p is empty, and every other shell is empty. Now you can say the lowest unfilled, or you can say empty energy band just above the valence band is called conduction band. Clear? So you can say again, like this is valence band. Let's suppose this is the valence band. Conduction band is what? The band which is just above it. Just above it, like after 2p, it will be something 3s. So that will be the conduction band. So this is the general representation. This is conduction band. As you move away from the nucleus, the energy increases. Energy keeps on increasing as you move away from the nucleus. So higher the orbit, higher will be the energy. That's why I have drawn conduction band above valence band. I'm repeating my words. You have seen it in the atoms chapter. As you move away from the nucleus, the energy keeps on increasing. So if energy keeps on increasing, so the energy, I am representing it from here. This is the lowest energy, I will say, lowest energy. Then in the above direction, if you move away or in the upward direction, the energy will increase. So that's why valence band will have low energy and conduction band will have higher energy, because conduction band is the band, or the band of higher level energy levels, of high energy levels. Clear? Okay. So you can learn few things from here, or make it clear in your mind that valence band and conduction band are drawn like this. Clear? Okay. One more thing which is very interesting. Now, I think it is clear to you that in valence band electrons are already filled and conduction band is empty. Clear? Now, if you give the atom some energy in the form of heat, in the form of light, any other form, if you can give some energy, then what will happen? After receiving the energy, the electrons from the valence band may jump to the conduction band. Are you getting my point? After receiving energy, electron may jump to this band. This band means conduction band. So after receiving energy, if you have given it some energy, the electrons may jump from conduction band to from valence band to conduction band. So I can draw it like this. Yeah. So electrons have jumped. They have reached the conduction band. Now listen to me again. Very simple things. When electron leaves the valence band, it will leave behind one vacancy of electron. And this vacancy of electrons is known as hole. This vacancy of electrons is known as hole. What is it called? Hole. Clear till now? Now, another point, another punchline I will say, that the electrons in the conduction band, the electron that has jumped to the conduction band is, or it behaves like a free electron. It is free to move. So the electron in this band is free to move within the solid. That means it behaves as a free electron, or you will say it behaves as a free electron. Things are different. It may create some sort of confusion in your mind if you are not focusing well. So I will repeat every bit that I have gone through till now. Number one thing, what we have studied, the energy bands. Energy bands forms due to the interaction of the shells. Clear? If you move, what are the conduction band? What is valence band? Valence band is the highest filled energy band, the energy band which is filled, and the highest band which is filled. And conduction band is what? Lowest band which is empty. Okay. How it can be represented? Valence band, and there is conduction band. Clear? Now, the punchline is, if you give the atom some sort of energy, then after receiving the energy, the electrons in the valence band may jump to the conduction band. Very simple statement I am saying. Electron may jump to the conduction band. In the conduction band, it behaves as a free electron. Keep it mind. Keep it in mind. It behaves as a free electron. Next point. When an electron jumps from valence band to the conduction band, what is left behind? A space is left vacant by it. And this space is known as a hole. It is a vacancy of the electron, which is generally known as hole. Clear? Till now, everything is clear. Now, moving further. Now, there is one more interesting definition coming our way, that is energy gap. Sir, what is energy gap? You can see we have drawn valence band, something like that, and conduction band, something like that. Clear? This was conduction band, this was valence band. Clear? The gap between them, the gap between them is known as energy gap. I think it is clear to you that these bands are nothing but collection of energy levels. So it is representing energy levels. Clear? So I am saying the gap between these two bands is known as energy gap, and sometimes it is known as band gap. Sometimes it is known as band gap. Clear? And this is the difference of energy levels. And if this is the difference of energy levels, its unit should be in the form of energy. And what is the unit of it? Is electron volt. Electron volt, generally represented as EV. Clear? Okay. Now it's time to make a particular definition. Okay. The difference between the lowest energy level of conduction band and highest energy level of valence band is called band gap. Now, someone of you might be distracted by the definition. Okay, I will make it very clear to you. First of all, just write it here. This is valence band, this is conduction band. Clear? Now, what you know, valence band is actually a collection of energy levels. So, like this is the collection of energy levels one, two, three, and four. These four are the energy levels of the valence band. Different energy levels. Similarly, conduction band is also a collection of some energy levels. Like suppose this is the collection of energy levels. So what is the statement? What is the definition? The gap or the separation between how you will define the band gap, the separation or the gap between the highest energy band, this one, of valence band, and lowest energy level of conduction band. This gap is known as, I think it is visible to you. This gap is known as band gap. This gap is known as band gap. Can you imagine, can you remember this definition? The difference between the highest energy level of valence band and lowest energy level of conduction band is known as band gap. How it is represented? It is represented by E for energy, G for gap. It is represented by EG. Clear? I think this is not a big deal. I have already told you the unit of this. This unit is electron volt. Other name is band gap. Clear? And this band gap is actually a very important parameter for this particular chapter. Whenever there is a question, you will see some questions related to this band gap. How? I will tell you. In the previous slide, what we have discussed that electron may jump from valence band to conduction band. Clear? So if electron can jump from valence band to conduction band, it may need some energy. This energy may be in the form of light, in the form of photons. You know that photons, light carries some photons. I hope you have studied that. So they will ask you what should be the wavelength of the light so that electron may make it transition from valence band to conduction band. They will give you this value. This value is of the order of few electron volts. They will give you this value and they will ask you how much should be the wavelength of the light used. Are you getting my point? We will give you some example based on it. So I think it is clear till now. Now based on this, Band gap, the materials are of three types. What are the three types? Insulator, semiconductor, and conductor. Three types of material we can define using this band gap. How? Very simple. Look at that. If I talk about conductors, in conductors, this band gap is either very small or negligible. You can say in conductors, this band gap is very small, like this. They just coincide with each other, like this. This is valence band, this is conduction band, and this gap is very small. You can say band gap is very small. What is the benefit of this very small band gap? You does not require much energy. What I am saying, if you need to jump from valence band to conduction band, this much energy is required. Is it clear to you? This much energy is required to jump, at least this much energy is required to jump from valence band to conduction band. And electrons in the conduction band are known as free electrons. But if you say in conductors this gap is small, that means at a very low temperature or very less energy, if you can give, the electrons can easily jump from valence band to conduction band, and that's why conductors can conduct more. And if I say for semiconductor, if I say for semiconductor, this gap is comparatively higher. This gap is comparatively higher. Comparatively higher with what? Comparison to, or as compared to the conductors, this gap is slightly higher. This is valence band, this is conduction band, and this gap is somewhat higher. Clear? And in insulators, this gap is very much higher. And if this gap is very much higher, now you can see that, or you can conclude that why insulators do not conduct. Now answer me, why insulators do not conduct? Because electrons most of the times doesn't have the energy to reach the conduction band. This gap is much higher, and electrons cannot jump to the conduction band. If electron is not in the conduction band, it cannot conduct. It is not behaving like a free electron. That's why insulators does not conduct at all. I think this particular phenomena is clear. The band gap is clear to everyone present in the class. Okay. Now, if I say this band gap is, let's suppose, EG1, this band gap is EG2, and this band gap is EG3. So what you can conclude, EG3 is greater than EG2 is greater than EG1. This is the conclusion that you can make from this particular slide. I think it is clear to everyone. Okay, moving further. Energy levels, then energy band, then what we have studied, the valence band, the conduction band, the energy gap. And based on the energy gap, the types of material, conductor, semiconductor, and insulator. And why insulator is behaving like an insulator, why conductors are behaving like a conductor, we can conclude it. I think everything is clear to you. Now moving further with another topic, types of semiconductor. This is again a very important topic. Before that, I should drink some water. Okay. So what I'm saying, intrinsic semiconductor. Types of semiconductor are what? Intrinsic and extrinsic semiconductor. In short, I will say intrinsic semiconductor are nothing but pure semiconductor. And these are impure semiconductor. We will discuss it. What is the meaning of this impure and pure semiconductor? So, in short, you can say intrinsic and extrinsic means pure and impure semiconductors. Now, coming back to the intrinsic semiconductor. Definition is very clear. The semiconductor in the pure form is called intrinsic semiconductor. Now, listen to me. I will explain few things here. The generally there are certain materials, certain elements which behaves as a semiconductor. What are these elements? You can say silicon, germanium. These are two widely used semiconductor materials, silicon and germanium. Just tell me in which group they are of the periodic table. In periodic table, what is the group of these elements? Okay, silicon and germanium. These are the basic materials. Now, if I talk about solid of silicon, there is a silicon solid. How its structure will be? Its structure will be something like that it forms a tetrahedral bond with the nearby silicon atoms. In the it forms covalent bonds in the form of tetrahedral shape. Like you can say this is silicon. In the outermost shell of silicon, there are four electrons. One, two, three, and four. Clear? And there will be other nearby silicon atoms. Something like that. It will also have four electrons. Another silicon, it will also have four electrons. Silicon, silicon, चारों तरफ सिर्फ silicon. So these silicon atoms forms covalent bond. One and one electron is shared, and they form some bond. Something like that. The chain continues to form. I am showing just one central atom. It is a long chain. Now, what you can say, this covalent bond is formed. Now, what happens in the band form? If you can see, the band structure will look like there is some conduction band and there will be some valence band. Now, just tell me, out of these two bands, which is valence band, which is conduction band? You can answer it. Which is valence band, which is conduction band? One will say, sir, the band which is lower is valence band, and the band which is higher is conduction band. So this is valence band, this is conduction band. Clear? Now what happens? This is the general semiconductor. Now some interesting thing will happen to it that you should remember. If I talk about, let's suppose at room temperature. At room temperature. Room temperature means 25, 26, 27 degrees Celsius. At this particular temperature, some of the covalent bonds will break. So the electrons, room temperature means some heat is there, some and external energy is there in the form of thermal energy is there. So due to this thermal energy, the bonds may break. And if a bond is broken, then what happens? One electron may jump out of by breaking its bond. And if one electron is leaving its bond, what will be left behind? You will say, sir, one vacancy will be created, and this vacancy is known as hole. Everybody knows that. And this free electron is free. So if I say in the band diagram, what will happen? In the band diagram, you can say some electron may jump from valence band to the conduction band like this, like this, and leaving behind a hole. Clear? Now, one more very interesting fact is that number of electrons are two, you can see here, and number of holes are also two. So what is the conclusion? That number of electrons is always equals to number of holes in the intrinsic semiconductor or in the pure semiconductor. This is a very interesting punchline. Clear? Yes, sir, clear. So in the intrinsic semiconductor, what we have discussed, that when, if I talk about silicon or germanium, these are the two very famous semiconductor materials. They are some artificial compounds which may behave like a semiconductor. I will discuss it later when we will be discussing about LEDs or some other special purpose diodes. So right now, silicon and germanium are two basic semiconductor materials. Now, what I say, how its structure will be, structure is in the form of tetrahedral shape. It forms covalent bond with the nearby silicon. Same structure will be for germanium as well. You can draw the same diagram for germanium by replacing silicon with the germanium. Same thing will happen. Now, at room temperature, what happens? These covalent bonds may break. How many covalent bonds will break, sir? Only 1% covalent bond or less than that covalent bonds may break at this particular room temperature. Clear? So how many electrons will be free? You can say very less number of free electrons will be available for us. Why? Because only a few bonds may break, and you can say that how much free electrons will be there? Very less number of free electrons will be created. Now, next punchline. Most of the times, if you say for any material, we are not interested in the uh, material. What require, we require some form of current. Why we are using some materials? We are using conductors for the current. We are using semiconductor for the currents. Semiconductors, where you can use semiconductors, if someone asks you, semiconductors are widely used in every electronic devices that you have, your mobiles, TVs, watches, anything digital you can see, it will have some semiconductors in it. Definitely. Clear? So for any semiconductor, for any device to operate, it needs some current. And if it needs some sort of current, then if I say how current can be created, in the third chapter or in the current electricity, you have learned that whenever there is a potential difference, then there will be a current. Now you have a material of semiconductor material and you have applied some potential difference across it. Like, so I will say, like you have applied some external field in this direction. Clear? Now listen to me very carefully. In this direction, you have applied some external field. Due to this external field, you can see this free electron will move opposite to the electric field. So this electron will move in the backward direction. Clear? Clear. Are you getting my point? This electron will move in the backward direction. Very clear, sir. Very simple statement. Now, what about holes? Now, look at that. Due to this external field, some of the covalent bonds, because this external field is applying some force, and due to this force, some bonds may further break. And if a bond breaks, for example, there is another silicon here. Just for example, I am saying this is another bond. And if this electron breaks, then this electron will jump to this hole. Are you getting my point? This elect and it will create a vacancy here, and this vacancy will be filled. I have applied some external field. This external field will apply some force. Due to this force, this weak bond may get broken. And if this bond is broken, then the electron which is ejected may jump to this vacancy. And if it jumps to this vacancy is filled and hole is created this way. So you can see that hole is moving in the direction of the electric field. So this hole is moving in the direction of the electric field. So can you imagine that hole is behaving like a positive charge, but actually it is not moving. You can see that hole is not moving. Actually, the electron was moving from another bond to this bond. Electron was moving, but in general, in short, we can conclude that electron moves opposite to the field, holes move in the direction of field, and conclusion may be written something hole behaves as a positive charge. Are they positively charged? No, they are not positively charged. They only behaves as a positive charge. Clear? Okay. So I am writing down the punchlines. Holes behaves as a positive charge. Another punchline. According to you, which is easy to move? Like electrons are easier to move or holes are easier to move? By the external field, obviously. Can you answer me? Answer me. Which is easier to move? These electrons are easier to move, or these holes are easier to move? You will say, sir, electrons are easier to move because these are the free electrons. The electrons in the conduction band are easier to move as compared to the holes. Why? Because actually holes are not moving, they are moving by the broken bonds. So you need more time, more energy to break the bond. So another punchline may be written as mobility of electrons in conduction band is higher than the mobility of holes in the valence band. Clear? I think all these statements are very much clear to you. Yes, sir, everything is clear. Done. Now moving further. Conductivity of intrinsic semiconductor. What is conductivity? How it is denoted? You can say conductivity is denoted by sigma. I hope everybody knows that. And sigma is what? J upon E. J is what? Current density. E is what? External field. Sigma is what? Conductivity. Now, if I break this formula, J is equals to N E V D by J. Clear? I hope you remember this formula from the current electricity chapter. The same I have used here. Now, this VD upon J is nothing but mobility. Vd upon J is what? Mobility. So sigma can be written as N E into mu. Mu is what? Mobility. I hope you know that. Vd upon J is what? Mu. Now moving further. I have told you on the previous slide that mobility of electrons is higher than the mobility of holes, and both of these are moving. So can you say that conductivity is not only due to the electrons, it is due to the electrons and holes both. So what will be the net conductivity? So net conductivity is what? Conductivity due to electrons plus conductivity due to holes. Net conductivity is due to both of these. So conductivity due to electrons is what? N E into mu E plus N E into mu H. Clear? What I have done? This is the formula for conductivity. I have placed it for electrons and placed it for holes. Now, if you can simplify it, sigma net will be, you can take Ne as common. It will be mu E plus mu H. This is the relation. All the JE students should remember this relation. NEET students as well. I hope this is clear to everyone. Is it clear? Simple statement. What is N? Number of electrons or number of holes? Because both are same, that's why I am not writing is that Ne or NH. Like you can see on the previous slide, I have written Ne and NH. Ne is the number of electrons, NH is the number of holes, but I am not writing Ne and NH separately because both are equal. So I have supposed it to be N. What is E? E is the charge of the electron. Holes behaves as a positive charge which with the same charge as the electron. That means E is the charge of either you can say electron or you can say hole. Same charge. Mu E is the mobility of electron. Mu H is the mobility of holes. So I can write what is mu here. Mu is the mobility. Mu is the mobility. Clear? So till now we have studied about intrinsic semiconductor. So it's time for a concept test. There is a question on your screen. You can take some 1 minute time, 1 minute time to solve it. In this 1 minute time, I will drink some more water. Okay. What is the question? Question says find the maximum wavelength of incident radiation which can create an electron hole pair in germanium of band gap 0.7 electron volt. Now listen to me. First of all, for the explanation purpose, question is very simple. It's a one liner. I will show you so that you can understand the things. What are these two bands? You will say valence band and conduction band. Everybody should remember this thing. Now, next thing, this band gap is what? 0.7 electron volt. Clear. And they are saying what is the maximum wavelength of incident radiation. So that means they are saying you are giving this semiconductor some sort of energy, and you are giving it energy in the form of photons. Radiation means energy you are giving in the form of photons. And after receiving the energy, electrons will jump from valence band to conduction band. And if electron jump, it will create a hole. So hole and electron pair will be created. So this energy they are asking, what should be the wavelength? So if you are giving energy in the form of photons, the energy is what? Hc by lambda. Clear? For lambda to be maximum, or you can say lambda can be written as hc by e. What is this band gap? Band gap, can you say it is the minimum energy difference of these two bands? Electron, you know that band gap is the difference, this difference is the band gap. If an electron jumps, it may jump from the lower or the lowest energy level of the band, valence band, to the highest energy level of the conduction band as well. So in this case, more energy will be required, and in this case, less energy will be required. So they are asking lambda maximum. For lambda to be maximum, E should be minimum. And what is the minimum gap between these two bands is known as band gap. Is known as band gap. So you can say lambda, for lambda to be maximum, it is hc by band gap. I hope this is clear to everyone. Now, what is the value of hc? You can say it can be simply put as 1240 divided by band gap is what? 0.7, and you can simplify it and you will get lambda maximum. You can simplify it. I am not doing it. Can simplify, 0 can be increased, and you will get 7 1, something like that. 1771.4 nanometer. I hope you remember this relation from the photoelectric effect, and the value of hc is 1240, energy in electron volt, then wavelength will be in nanometer. I hope you remember this relation. So maximum wavelength should be 1771.4 nanometer. I hope this is clear. So this is it from this lecture. In the next lecture, we will discuss further. Till then, bye everyone. Bye.